previous videos we've been setting up some of the intuitions and axioms behind set theory, but in this video we're going to begin rigorously defining some of the more familiar objects in math, such as the notion of an ordered pair, and eventually we're going to also set up the notion of a Cartesian product. And these two basic ideas are going to eventually allow us to start to talk about things like functions and relations. So in our basic notion of a set, we're used to talking about a set as just a group of objects sort of put together into one collective. And one of the basic properties of a set is that it's unchanged by changing the order of the elements within it. So to be clear about that, so suppose I had the set A and it had these two members in it, the number 1 and the number 2. So suppose I consider another set which is related to it, let's say B, and that has the objects 2 and 1 in it. We still say that the sets A and B are the same set, even though the order is being flipped between the two sets. So this leads to this notion of pairing. So with sets, these two objects 1 and 2 are paired together, but they are unordered, in the sense that if you change the order of the two elements, we're still saying that the sets are the same set. So we're going to say that sets are an unordered pairing between the elements 1 and 2 in this case. But suppose we want to start talking about ordered pairs. So let's consider two ordered pairs. Let's say I have the ordered pair A, which is going to be represented by these angled brackets. So I'm going to use this notation from now on. The angled brackets containing the elements 1 and 2. And let's consider another ordered pair B, which contains 2, 1. Now, in our notion of sets, as we saw in the previous slide, we would consider the sets containing 1, 2 and the set containing 2, 1 to be the same set. But in our notion of ordered pairs, we don't want to make the statement that 2, 1 is the same as 1, 2. And you can kind of see where this is going in the sense of ordered pairs, and this is eventually going to lead to the intuition of a point on a coordinate plane. And from our mathematical experience, we don't say that the point 2, 1 is the same thing as the point 1, 2. So we want to start to get this intuition of an ordered pair clear, and also rigorous in the sense that we want to give a set theoretic definition. So the more general statement that we want to say is that if we have some ordered pair, let's call it A, having xy in it, and some other ordered pair B having yx in it, we don't want to say that A is equal to B. And the only case we want to say that A is equal to B is in the special case that x is equal to y. So for example, if you had 1, 1, if you flip the order like that, it's just the same thing. So that in that case, we can say A is equal to B. But in general, we don't want to say A is equal to B in the case where you flip the elements around. So as I said above, we need to start thinking about how we're going to represent this new notation with the angled brackets, which is going to denote an ordered pair in terms of sets, because we're trying to build a rigorous definition of more familiar mathematical objects such as ordered pairs by using sets. So that's going to be our next goal, to provide a rigorous definition of ordered pairs in terms of sets. So one thing to point out is that in our set theoretic definition, we need a very important property of the ordered pair, which is kind of what we were hinting at before. That's to say that if two ordered pairs are equal to one another, this should only be true if the first component of the ordered pair is the same, and that the second component of the ordered pair is the same. And vice versa. If we have both the components being the same, then we say that the ordered pair is the same. So this is the key property that we're going to need in setting up our set theoretic definition of ordered pairs. So let's take a first stab at setting up some sort of set theoretic definition. Let's say we just define an ordered pair xy as the set containing xy. Now, what we said before in the previous slides is that we know this definition is not going to work, but let's go through why it's not going to work. So if I had the set xy, we've already said before, this is the same thing as having the set yx. And if we're going to use this definition, the set yx can be represented as the ordered pair yx. So we can see that in this deduction, that if we're going to set up the definition of an ordered pair as such, then the ordered pair xy is going to be the same as yx. So we haven't captured this fundamental property quite yet, unless we have in the special case that x is equal to y and y is equal to x. So we see that this is not going to work as a definition of ordered pairs. So to summarize thus far, we need this key property of the equality between ordered pairs, and we also don't want to make this sort of statement that any arbitrary ordered pair xy is going to be the same thing as yx. So with those two necessities in mind, let's make a second stab at setting up a set theoretic definition. So let's say we say that an ordered pair is a set containing x as its first member, and the second member is going to be the set containing y. So let's work with that. And just as a hint, this won't work also, but to provide a counterexample to this, or to provide an example that's going to dissuade us from adopting this definition, let's take the example where I have the first component being the set containing 1, and the second component being the set containing 1 as well. So from our set theoretic definition, we can say that this is equal to the set containing 1 as its first element, and the second element is the set containing 1. So you can just see that I'm just sticking another set of parentheses around the second component here. And from what we said before in sets, we can just switch the order around. So I'm just going to take this set and switch the order. I'm going to put that element with two parentheses around it as the first element here, and then the one with one parentheses around it as the second element. But if I just apply the definition one more time, I could just remove the set of parentheses from the second element here, and that becomes the second component of the ordered pair. So what I have in conclusion, if I adopt this definition, is that this ordered pair here is going to be the same thing as this ordered pair here. So this is another property that if we adopt this definition that we don't really want to say. So we're not going to adopt this definition. And you can see that if we're saying these two ordered pairs are equal, it's pretty obvious that this first component is definitely not the same thing as this first component. And the second component is not the same thing as this component. So these ordered pairs really aren't going to have that key property that we want. So this won't work as well. So our third and final attempt at a set theoretic definition of ordered pairs is going to culminate in what's called the Kuratowski definition. So this definition, what it's going to do is going to say that an ordered pair xy is equal to the set containing as its first element the set containing x here, and as a second element the set containing xy. So already this is a pretty elegant looking definition here, because we can see that the xy is sort of contained within it, and that this element here, which only has one member in that set, is going to sort of pick out which one of those two from this here is going to be the x value. So as a spoiler, this definition will work. So what we're going to have to do is verify that this definition satisfies this key property, that in order for two ordered pairs to be equal to one another, what we need is that the first component of both ordered pairs is to be equal, and that the second component of the ordered pair is to be equal. So what we need to do is verify this if and only if statement. So just like what we're familiar with the logical statement if and only if, we need to check the left to right hand side statement and also the right to left hand side statement. So we have two statements to prove. First, that x is equal to u and y is equal to v implies that this ordered pair xy is equal to the ordered pair uv. And secondly, if it's true that the ordered pair xy is equal to the ordered pair uv, then that implies that x is equal to u, that the first components are equal, and y is equal to v, that the second components are equal. So this first statement here is pretty easy to see, because if x is equal to u and y is equal to v, then xy can be written as uv. So I just get the statement uv is equal to uv. So those are the same thing, and we're just going to leave it at that. So that statement is pretty easy to prove. The second statement here, that the ordered pair xy being equal to uv implies that x is equal to u and that y is equal to v. This is going to take a little bit of work to justify, but it is worth going through just to see that this Kuratowski definition will work as a definition for ordered pairs. So let's go about showing that. So let's assume that we have this ordered pair uv being equal to the ordered pair xy. So if that's true, then that implies that this set here, which is just the Kuratowski definition for uv, is equal to this set here, which is a Kuratowski definition for xy. So to approach the proof, we're going to take two separate cases. So first, we have the case that in this ordered pair uv, that the two components u and v are either the same thing or that they're different. So let's suppose that they're the same thing, that u is equal to v. So using the Kuratowski definition, I can just substitute u for v. So I'm going to get u here, and then as the second member I'm going to get the set containing u. And if you just work that out, then this is the same thing as the set containing only the set containing u. And since this whole statement here is true, then this set here, the set containing the set u, is equal to the set containing x and also the set containing xy. So this statement here, the equality between these two sets, implies that u is equal to x and that u is also equal to y. So the conclusion we have so far is that u is equal to x, which is also equal to y. And from the above assumption, we have that u is equal to v. So all four of these objects are equal to one another. So we have u is equal to x, which is equal to y, which is equal to v. So that means we have the two equalities that we need to complete that section of the proof. We have that u is equal to x, which is right here, just u is equal to x, and that v is equal to y. So that means if u is equal to v, then we have those two properties that we need. That the first components have to be equal, u is equal to x, and that v is equal to y. So now let's take the case in which u is not the same thing as v, that u is not equal to v. So, in order for these two sets to be equal, this set here on the left and this set here on the right, remember that in order for two sets to be equal to one another, every member of this first set must also be found somewhere in the second set, and vice versa, that any member of the second set must be found within the first set. So if I pick this element here, the set containing u, this must either be equal to this element here, the set containing x, or it's got to be equal to the set containing xy. It's got to be equal to one of those two. So that's why I say here that this statement or this statement has to be true. And it also must be true that the set containing uv has got to be equal to x, or that it's got to be equal to the set containing xy, for the same reason, that all members of the first set have got to be found somewhere in the second set, and vice versa, that all members of the second set have to be found somewhere in the first set. So in summary, that if these two sets are indeed equal to one another, if that statement is true there, then this entire statement must be true. Now let's sort of figure out what's going to happen if some of these statements, some of these individual statements, such as the set containing u is equal to the set containing xy, are true. So let's first take that case, that the set containing u is equal to the set containing xy. This statement implies that u is equal to x, which is also equal to y. And this in turn implies that this set containing, first the set containing u and the set containing uv is equal to the set containing x. Why is that true? Because x is equal to y, and if I go up to here, to this big set, I can just substitute x in for that y there, so I get this double braces x. Now if this statement is true, then x is equal to u, which is in turn equal to v. And remember, we started with the assumption that u is not equal to v, and we've just derived the contradiction here because we said that u has to be equal to v. So since we derived the contradiction, this can't be true. So this entire proposition that the set containing u is equal to the set containing xy can't be true. So that's one proposition that can't be true in this entire statement here, right here. So let's now take this second proposition here, that the set containing uv is the same as the set containing x. Now that implies that u is equal to v, which is also equal to x. And this is again a contradiction because we're now saying that u has to be equal to v. All right, so that statement right there, that the set containing uv is equal to the set containing x, is also going to lead to contradiction. So what we're left with is this first statement here, that the set containing u is equal to x, and with this fourth proposition here, that the set containing uv is equal to the set containing xy. Now since this entire statement has to be true, and we have this and operator here, that means that these two statements have to be true. They have to be both. They have to be true at the same time. So what we know is that u, the set containing u, is going to be equal to the set containing x, and that the set containing uv is equal to the set containing xy. So what does that imply? So this first statement that the set containing u is equal to the set containing x implies that u is equal to x. So what that means is that I can substitute u for x in this second equality here. So I'm just going to take that x right there and stick in a u. So I get the set containing uv is equal to the set containing uy. Now, if I take that element v there in the first set, since these two sets are equal to one another, v must either be equal to u or it must be equal to y. Because remember, for two sets to be equal, any arbitrary member of one set has to be found somewhere in the other set. So that's what I'm saying here, that v is either equal to u or that v is equal to y. Now, since again, v equals u leads to contradiction, because that's violating our assumption here, v must be equal to y. So let's look at what we've done so far. We've said that in the case in which u is equal to v, we're guaranteed the two statements that u is equal to x and that v is equal to y, which is what we want. So that case is settled. Now suppose that u is not equal to v. We've now shown that if that's true, that u must be equal to x and that v is equal to y. So in summary, we've got the key property that we need, that for two ordered pairs to be equal to another, that means that their first components have to be equal, that u is equal to x, right here, and that v is equal to y. So we've basically shown that. So again, to summarize what we've done so far, we've successfully represented an ordered pair as a set by the Kuratowski definition, which is, just to remind you, that the ordered pair xy is equal to the set containing x as the first member, and as the second member, the set containing xy. And we've shown that it has that characteristic or key property that we need. And one thing to point out here is that in this definition, there was no mathematical necessity that said that you must set up the ordered pair xy as this particular set. So this is an arbitrary decision, but we've shown that it works. And since it was arbitrary, you would suspect that there are other representations in terms of sets that would also work. Just looking around on the internet, this is another representation that would work. And I think this is one of the older definitions before it was found that the Kuratowski definition is mathematically fine. So this is another set theoretic representation that would also work. And I challenge you to find some other ones that would also work. But this is a very concise way of representing an ordered pair as a set. So this has become the standard definition of ordered pairs as sets. So for simplicity, we're going to stay with the Kuratowski definition of ordered pairs. Since we've given a rigorous justification for what an ordered pair is, let's start to build upon that and see where that leads. So suppose we have two sets. First, the set A containing 1, 2, and some set B containing 3, 4. Now, let's think about all the ordered pairs that I can form by using these two sets A and B. So what I'm going to do is I'm going to pick some element from A, call that the x value, and then I'm going to pair it with some y value from the set B. Now, if I do that process, just pick an x value from here, this first set A, and pick a y value from this set B, you can see that there are 4 possible ordered pairs that I can form. So I could make my x value be equal to 1, and then I have 2 choices for y. It can either be equal to 3, or it could be equal to 4. So that gives me 2 ordered pairs here. Or I could let x be equal to 2, and then again I have 2 choices for the y value. I have y equals 3 or y is equal to 4. So in summary, I have 4 possible ordered pairs that I can form from starting out with the sets A and B. So what I'm going to do is take all these 4 ordered pairs and put them into a set. And let's call that set R. So what have we just done? We've taken all possible ordered pairs from 2 sets A and B, and we formed another set R containing all of those possible ordered pairs. So it turns out that what we've just done is called we formed the Cartesian product A times B. So in the abstract sense, what the Cartesian product A times B is going to be, it's going to be the set containing all possible ordered pairs x and y, such that x is a member of the set A, and that y is a member of the set B. So this is a big step in our talk of set theory, because the Cartesian product is going to eventually allow us to talk about things like relations and functions. So one way to think of this process that we've just done between 2 sets A and B by forming the Cartesian product A times B is that we've set up a grid using the two sets, and that within this grid we have a number of points, now by taking the elements of both of the sets. So just to be clear about that, I pulled these two pictures from Wikipedia. So if you go on Wikipedia, look up Cartesian product, this is what you get for some of the images. So let's say I have some set A, has three members, x, y, and z, and I have another set B containing 1, 2, and 3 as its elements. Now let's do that same operation, form A times B, the Cartesian product A times B. So what I'm going to do is pick an x value from the set A, and then you see here I have three possibilities for the y value, so I can form three ordered pairs from that. So I have x1, x2, and x3 as three possibilities, three members within A times B. And I just repeat that for all the other x values to be found within the set A. So hopefully you can see that if the set A has, let's say, m members, and that the set B has n members, then A times B is going to have m times n members. And this is going back to what I was saying about forming a grid between two sets. To make that super obvious, let's consider something we're all familiar with, which is the two-dimensional Cartesian plane with the x and y axes. So you can see here that what I really have here is a grid containing some selection of an x value from the horizontal axis and some value for y on the vertical axis. So going back to what we've been talking about with Cartesian products, I can sort of abstract this in saying that I've got some set containing all the members found on the horizontal axis and some other set containing all the members on the vertical axis. And all the possible order pairs I can form between x and y will be given by all the points that you can form by sort of intersecting all the lines drawn through some element of x or y. And you can see that this leads to our common definition of plotting points on a coordinate grid. So this is sort of why we're interested in providing a rigorous definition of this, because we can go from the ideas of set theory to the more common sense notions of something like a coordinate plane. So here's one last interesting property about order pairs before I conclude the video. So suppose I have some set A, and let's say I draw two elements x and y from the set A. So x is a member of A and y is a member of A. Then what follows from that is that the order pair formed by x and y is a member of the power set of A. And this is kind of interesting because we can sort of justify where this order pair exists by using the power set axiom. So if we get some set A, we can just take the power set twice, and we can say that the order pair x and y is most certainly located in the power set of A. So here's the proof of that statement. So if x and y are both in A, then that implies that the set containing x is a subset of A, because all of the members of this set here on the left are also members of the set A, right? And that the set containing x and y is also a subset of A. And from those two statements, it follows that the set containing x and the set containing xy are both within the power set of A. So if I just take these two elements here, there and there, and just throw another set of parentheses around that, so I have the set containing x and the set containing xy, that's also a subset of the power set of A. And if that's true, then this whole thing must be a member of the power set of A. And it just follows from that the order pair xy is a member of the power set of A, just utilizing our Kuratowski definition of what an order pair is. And two other interesting facts that this implies is that if we have this property here, what we can then say is that the Cartesian product A times A is a subset of the power set of A. And furthermore, that the Cartesian product between two different sets, A and B, is a subset of the power set of A union B. And those two statements I'll leave for you guys to prove as an exercise. So here are the practice problems for this lecture. And in closing, one thing I just encourage everyone to do is that really try to form an intuition behind what a Cartesian product is. In terms of the way I think of it is just setting up that grid. Well, if you can find some other interpretation that works for you, that's perfectly acceptable. But this is a sort of a neat property of set theory that I really encourage you to try to develop your own personal intuition behind. And stay tuned for the next video where we'll start to talk about functions and relations, And as always, if you enjoyed the video, like it or subscribe, and I'll see you next time.